when you're being taught about elementary particles, you're unlikely to hear that muons are mesons. Well, they are in onium theory, which is also not taught. And so it's been known since 1965 that muons are not elementary particles, that they're composite particles. And to begin with, to understand muons, we also have to understand pions. Now, my last video I did was on the neutral pion. And a neutral pion is a relativistic electron-positron pair. It's relativistic positronium. And there's a solution that is ignored by a quark theorist because it would blow up the quark theory. That if you have an electron and positron orbiting at relativistic velocities, they can have a metastable state that happens to have the mass of the neutral pion. So there's a far simpler way of describing the neutral pion than the one in the quark theory. So we can start with, to understand the Onium theory, is a muon and a pion have the same composition, but they have different energy. And because of the difference in energy, when a muon decays, it decays to an electron. So at least externally it looks like an excited electron, maybe. While the pion, on the other hand, can decay to a muon or an electron, but it also can decay to a neutral pion and an electron or positron, depending on the charge of the muon. And so the muon-electron decay mode actually gives us a hint as to what the pion is made of, and the muon as well. So the energy difference, though, the mass of the muon is 105.65837 MeV per c squared, while the mass of the pion is 139.57018 MeV per c squared. So when a muon decays, it does not have enough energy to produce a pion. So it produces an electron, and the rest of the mass, it gets lost into the quantum field. While when a pion decays, it can decay into a muon. So we have a situation where if you look at all the particles, of all the mesons in particular, they decay into lighter and lighter particles. But just because the muon happens to be the lightest meson in the decay chain doesn't make it a lepton. It doesn't make it an excited electron. So we can look at it two ways, and the traditional way is the muon being an excited electron, but the other way is that it's the lowest energy meson. And in this Onium theory that I've been trying to advance because it's far superior to quark theory, the muon is the lowest energy meson. Now, the first person to recognize this was Ernest Sternglass, and he published about it in the early 60s. And what he recognized is that, as I said, you have a pion and an electron orbiting each other. And this is non-relativistic orbit, because while the pion internally has a relativistic electron-positron pair, the extra electron is not relativistic. If the extra electron were relativistic, it would add additional relativistic mass energy to the compound, which would create a different resonance. And so if we break it down, we can have the neutral pion in the middle, orbited by an electron. And the difference in energy comes about because of the difference in orbital direction. If the electron is orbiting in the same direction relative to the internal neutral pion orbit, that's the lowest energy state. And if the electron's rotating opposite the neutral pion, that's the higher energy state. So we have two states of these neutral pion electron compounds, depending on the orbital direction. In one state, the mass energy equals the muon. And in the other, the mass energy equals the pion. And so, in this way, we can develop a theory of, an Onium theory of particles, in which the muon and pion are related, and they're mesons. Now, there's another type of muon that was discovered later by Peter Finley Brown, and he published about in 1981. He realized that instead of having an electron in orbit with a pion, you could instead have the pion orbiting around the electron in a more direct way, where you have an electron in the middle being orbited, which is slightly different, but it has the same mass energy. And what occurred to me when I was looking at these two different models for the muon is that perhaps that would explain why some muons have a longer lifetime. As you may be aware that there are cosmic muons that form in our atmosphere but can reach the ground and can have much longer lifetime than a muon in an experiment. And now this is normally said to be due to relativistic clock slowing by the muon. There have been some physicists who have wondered if there are two muons with different lifetimes. And in the Onium theory, that's exactly what it appears we have, is two muons with two different lifetimes. Anyway, I'll be talking about other Onium compounds as I develop the Onium theory further in a series of videos I'm doing on it. But it's key that we understand that muons are mesons, which means that muons are not elementary particles, which changes the way we look at a lot of things, even neutrinos. Because under neutrino theory, if you needed a muon neutrino, you would basically need a different neutrino for every meson and every baryon, which is not a viable theory, which is why we need to come up with a simpler neutrino theory. And I'll talk about that in another video. So anyway, if someone tries to tell you that muons are elementary, you can say, no, they're not. There's a model for them that they're electron and a neutral pion in a compound. And so anyway, I hope you enjoy this video. If you do, please like, share, or subscribe. And if you're interested in reading more about it, you can buy my book, The Goodbye Quarks, The Onium Theory. And if you're interested about quantum field theory, as I normally do my research on, I have a couple other books that are also available for sale. And if you buy a book, that helps support me. I'm an independent researcher, so I need support. I also have a Patreon account. I want to apologize for the motorcycles being noisy at 7 a.m. on a Saturday. So, I hope you enjoyed the video anyway. Thank you.